So in this lesson, we're going to start putting together a lot of things that we've been doing over the past couple of units about getting information about the shapes of graphs. And we're going to put it all together to the point where we're actually going to start sketching the graphs of functions. So what we want to be able to do by the end of this lesson is to be able to sketch the graph of a function using the intercepts, the x and y intercepts, the asymptotes, the local maximum and minimum values, the points of inflection, the information that we have on the intervals of increase and decrease, and the intervals of concavity, and any other information that we might have that is easily available about the shape of this function. So we're going to do these things in a specific order. Okay, and this is sort of the order that we are going to do them in. And this is straight out of the textbook. It says do them in this order. And when you get to the test is going to say to do them in this order, and these steps are going to be listed for you. So you don't need to copy this down. I'll write down these steps as we go through the example. And as we go through the examples, I think you'll see why we do them in this order. So first we're going to look at the domain of the function. Then we are going to look for the asymptotes and possibly the end behavior of the function. Then we're going to find the intercepts. Then 4 and 5 we kind of do together. We find the turning points and the intervals of increase and decrease at the same time using the first derivative test. And then we'll do the points of inflection and the intervals of concavity kind of at the same time by setting up our interval table using our second derivative. And then this last step at the end is sort of an optional step. Usually by the time you get to the end of step 7, you have enough information to sketch the graph of the curve. Often by the time you get to the end of step 5, you have enough information, but it's good to do step 6 and 7 just as sort of a check. If you get to the end of step 7 and you're really not still sure about what the function looks like, you can see if there's some other information that's going to help you do it. But usually you're good to there. So let's just consider an example here. And I'm not going to do that example. I'm going to do this example here. Okay? The first example was a polynomial function. This is not a polynomial function. This is going to be a radical function. Okay? So we want to sketch the graph of y equals x times the square root of 2 minus x. And to do this, we are going to do, well, all of those steps that we had listed before. We're going to need our first derivative and our second derivative. And as I mentioned in the last lesson, the first derivative and the second derivative are going to be given to you in this case. Okay, so you don't have to go through the work of calculating them. Your job, though, is going to figure out what all of to go through those steps and figure out the needed necessary information. So let's start with the domain of our function. That was step 1. Looking at this function, y equals x times 2 minus x, what is our domain here? And by domain, we mean what possible x values can we put into this function that are going to give us sensible y values at the end of it. So really what we're asking is, normally our domain is x is an element of all the real numbers. And then typically sometimes we have a restriction on our domain. Is there any x values that are not good?
Anything above 2.
Why not anything above 2? Yeah, we'll get a negative number underneath that square root symbol, and so that is a no-no. Now, I've written down x must be less than 2. Can it be equal to 2? Is that okay? I see some of you shaking your heads and some of you nodding. Okay. So if x is equal to 2, we will have 2 minus 2, we will have 0. We'll be taking the square root of 0. Can we take the square root of 0? That's fine. It just gives us 0. So it's not a particularly useful number, 0, but it's a valid number. So x must be less than or equal to the number 2. So next up, our intercepts. We want 2 intercepts here. We want our x-intercept, and we want our y-intercept. And we find our x and our y-intercept by setting one of our variables equal to 0 and then solving for the other one. So if we want our x-intercept, we are going to set y equal to 0 in our function and solve for x. So if we set y equal to 0, we get 0 equals x square root of 2 minus x. And we have to think about. So what values of x can we put in there that are going to give us an answer of 0? Well, ordinarily when you're solving a question like this, you would have to factor it, right? Set it equal to 0, factor it, set each of your factors equal to 0, and then solve for x. So we've got this in factored form already. It's x times 2 minus x. So what are our solutions here? Yeah. X equals 0, and x equals 2. So our intercepts are going to be the point 0, 0, and the point 2, 0. What about our y-intercept? Well, for our y-intercept, we are going to set x equal to 0 and solve for y. So if we set x equal to 0, we get y equal to 0 times 2 minus 0, so that's just going to be 0. So our y-intercept is the point 0, 0. Okay, so we've got that point 0, 0 is both an x-intercept and a y-intercept. Step 3, asymptotes / end behavior. So we want to check to see if we have any vertical asymptotes, whether we have any horizontal asymptotes. We get vertical asymptotes when in rational functions, when we set the denominator equal to 0. We don't have a denominator here, so we can't set it equal to 0, so we're not going to have any vertical asymptotes. And in fact, we are not going to have any horizontal asymptotes either. But what we do want to do is consider the end behavior of the function. And we talked about this a little bit back in Unit 9-10 where we're working with those limits. What we want to examine here is what is the limit as x tends to positive infinity of our function and the limit as x tends to negative infinity of our function. And instead of our function, I could actually write the function in here. So x root 2 minus x, x root 2 minus x again. Okay. So, what happens as x tends to positive infinity? Well, let's do the second one first. Let's see, what happens as x goes to negative infinity? Okay. So what we can imagine is making this first x value here a very, very large negative number. Okay, so that term is going to get larger and negative. Okay. What about inside the brackets here, this term? Well, if x is a very, very large and negative number, if we do 2 minus that large negative number, that's going to be like 2 plus a large number. So we're going to get a large positive number in there, and we're going to take the square root. So it's like this is going to tend towards positive infinity, okay, as we make x larger and larger and larger. Our first term, because it's just x, it's going to tend to negative infinity. So our limit is like negative infinity times positive infinity. So infinity times infinity is just infinity. Negative times positive is just negative. So our function is going to tend off towards negative infinity. Basically, it's just going to keep going down, 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 down. Let's go back to the first one here. What happens if we put positive infinity in there for those x's? The first one is just going to go to positive infinity. What happens if we put a very, very large positive number in for that x in the second term. Maureen, am I? Because what do I have to do? I'll get 2 minus a very large number, which will give me a larger and larger and larger negative number. But then when I go to take the square root of it, I have problems. I'll get an imaginary number. So this term basically doesn't make any sense as we go to larger and larger x values. How can we make sense of this? Well, let's go back to step 1. The domain of our function is that x has to be less than or equal to -2. So we actually can't make x go to positive infinity with this function because positive infinity is much bigger than 2. Okay? So we don't actually have to consider the end behavior as x goes to very large numbers because of our domain, x is never going to go to very large numbers. It's going to stop at 2 and not go any further. Does that make sense? Okay. So that's kind of why we do the domain first before we consider anything else. Okay. Where are we here? We are on to intervals of increase and decrease, or maximum and minimum values. So let's just say, what step are we on? Let's do 4 and 5. Okay. If we're looking for maximum and minimum values, we're going to look for our critical numbers, where our first derivative is equal to 0, or our first derivative does not exist. So what is our first derivative here? Well, our first derivative is 4 minus 3x all over 2 times root 2 minus x. Okay, so if we're setting this equal to 0, let's say this f prime at x equals 0. We are setting the numerator equal to 0, so 4 minus 3x must equal 0. And then we're going to solve this thing for x. So we'll get negative 3x equals negative 4. X equals 4/3 is one critical number. What about where our derivative does not exist? Well, it's not going to exist where the denominator equals 0. So let's take our denominator and set it equal to 0. Well, let's see. We can divide both sides by 2 to get root 2 minus x equals 0. We can square both sides to get 2 minus x equals 0. And we can get, and then we can rearrange this and get x equals, not x, but 2. So our derivative doesn't exist at the point x equals 2. Okay. Now, this point x equals 2 has come up before. And what's special about this point x equals 2? Well, it was the point that was at the very end of our domain. Okay? Beyond x equals 2, our function doesn't exist. So really, this critical number here is simply telling us that something weird is happening at x equals 2. Okay? It's the end of our domain. So chances are this is not a local maximum or a local minimum. It's actually just this point where weird stuff happens because our function stops. So to confirm whether or not these critical points are in fact local maximum or local minimum, that's where the first derivative test comes in. So we need to set up an interval table here. Our intervals will go from negative infinity to 4/3, and then from 4/3 up to 2, and then we don't have to go any further because our domain is restricted. We know our function doesn't go beyond there. And what are we doing? We are checking the sign of every term in our first derivative. So we've got 4 minus 3x, and we've got 2 times root 2 minus x, our numerator and our denominator. And again, with the first derivative test, what we're looking for is, what is the sign of the first derivative? What does this tell us about our function? So if we look first at 2 times root 2 minus x, we have restricted our domain so that we are always going to be taking the square root of a positive number. So we know that if we're taking the square root of a positive number, we're always going to get a positive number. And if we multiply it by 2, it's still going to be positive. So this term is going to be positive no matter what we do. Okay? And remember, you can always check this by taking a test value from your interval, just subbing it in and see whether you get a positive or a negative number. Okay? What about 4 minus 3x? Well, let's see. If we put in something from our first interval like 0, we get 4 minus 0, which is 4, which is positive. If we put in something from our second interval, like 2, let's say, because that's included in our interval, we would get 4 minus 6, which is negative 2, so this is going to be negative. So our first derivative is positive, then negative. So our function must be increasing and then decreasing. So we have one local maximum here. At 4/3, and then we work out what the y value is going to be, 1.088. Now, we actually have enough information right now that we can sketch the graph of this function, but we're going to go ahead and we are going to do the concavity table anyways, just to see what it looks like. So 6 and 7, I'll just call this concavity. If we're doing concavity, we want to check where our second derivative is equal to 0. Our second derivative does not exist. So we've got the second derivative way up there at the top. We just want to set, if we're looking for where the second derivative is 0, we're setting the numerator of our second derivative equal to 0. 3x minus 8 equals 0. And we're going to solve for x. We get x equals 8/3. Now, does somebody have a calculator? Work out what 8 divided by 3 is. .6. So is this a point where our concavity can change? Marina is shaking her head. Why? Yeah, it's outside our domain. So we don't even have to consider this point anymore. We could just say, hey, not in domain. Okay? Which is another reason why, hey, that's why we do the domain first. Because sometimes we will get values that, that don't seem sensical here. If we're looking for where our second derivative does not exist, let's see, we want to set the denominator, which is 4, 2 minus x to the 3 over 2. Again, denominator of our second derivative equal to 0. The solution here is going to be x equals 2 again. So once again, we're getting this weird point where our domain ends to be one of our critical numbers here. So really we only have one interval from negative infinity all the way up to x equals 2. So let's just make sure we check what the concavity of our curve should be here. So again, our two terms out of our second derivative. And we want to know, hey, what is the sign of our second derivative? What does this tell us about the concavity of our function? So imagine subbing in a test value of x equals 0. We are going to get -8, which is clearly negative. If we sub in 0 here, we're going to get 2 minus 0 is 2. Whatever rooting or squaring we do to this is going to be positive. Multiply it by 4 and it's still positive. So our second derivative is always going to be negative. So if our second derivative is negative, is our curve concave up or concave down? Concave down, yeah. Second derivative negative, concave down. Okay. So let's put all of this stuff together, sketch the graph of our function. Okay. So on the test, you'll see a grid that looks something like this, so you can sketch it a little bit accurately. So let's start with the domain. We know that our domain goes up to, maybe I'll do this in a brighter color here. Our domain stops here at x equals 2. So our entire function is going to be sort of to the left side of this graph here. Our intercepts were 2, 0, okay, which I've just put one of those intercepts right there. And our other intercept was at 0, 0. We found that as x goes off to negative infinity, our curve went off to negative infinity. So our curve has to end up way down here like this at some point. Okay? As x goes off to negative infinity, is it like negative infinity is out down here? Y itself is going off to negative infinity. We found a single local maximum at 4/3 and just a little bit bigger than 1. So this was our local minimum point. 4/3, I think we found 1.088 as our local minimum. And we found that our curve was increasing and then decreasing. In terms of our concavity, we found that our curve was always concave down. So we need to draw a curve that goes through these points, is increasing and then decreasing, and is always concave down. So this is pretty simple in this instance. It's just going to look something like that. And that's our function.